All right. Uh, so today is I don't know. Today is May 27th. All right. So um, we are going to do some. We're going to start with some midterm review. So you should have gotten your assignment twos submitted. That server has been closed now. The assignment three, I expect to have the server up tomorrow. Of course, these things usually take longer than you think, so uh, I'm fingers crossed it's tomorrow, but otherwise by the end of the week for sure. Of course, the big news is the midterm on Thursday. This is like a half class, right? So the midterm is 80 minutes, and then after there's no lecture. It's just, too much coordinating. If you're done in 20 minutes, then you have to wait an hour for the rest of the lecture, and it's just silly. So, and there's also people writing in the PMC who would miss the lecture altogether, and so it's just easier just to have sort of a half class. Um, so yeah, that's it in terms of things that you have on your agenda, the midterm study and tutorial three, if you're really eager to get started. Assignment three will be on skip lists. Should be sort of challenging, but hopefully you've warmed up on regular linked lists. Super similar to the practice, yes. Super, really, if you can do the practice, you can do the midterm. Okay, so I think that's where we stand. Any questions? Okay. Yeah, no surprises, eh? I'm not trying to trick anyone. Um, I'm trying to tell you exactly what's going to be on it. It's your job to study and learn that stuff, and then kind of regurgitate it, spit it back to me. Actually, none of these are great visuals, but do the midterm. So we're gonna walk through and see what we mean by all these questions. I'm gonna explain them, and then how to answer them. And what you see on Thursday will be very similar to this, with some numbers changed and or the functions change, right? But again, I'm not here to trick anyone. Here to hopefully you're going to learn this stuff, and so yeah. All right. So to get started is I think there's 9 questions on the practice, but there will be 10 on the actual midterm. But it's on, generally speaking, these sort of simpler versions of data structures, list-based data structures, essentially. So based on array-backed data structures or linked list data structures. And so just to describe, we define a fundamental operation to be either copying a piece of data from one location to another, or updating a reference or traverse from one node to another, as you do with a linked list. So this is essentially going to be how much work do we have to do for these calls on these data structures. So for example, and of course we want to round it off. So you could think of this as a multiple choice question where the choices are 0, 100, 200, up to 1,000, right? There's no other answers. Those are the only answers you have. So you have basically 10 choices for each of these questions. So calling add 800x on a singly linked list, how much work do we have to do? That's the answer here. Yeah, 800, yeah. So why is it 800? Well, if you recall, on a singly linked list, if I want to get to location 800, I have to walk there. And if I want to add, and then once I get there, I can insert, let's say I have this structure and I want to add something. Well, that's going to be 1 or 2 operations, redirecting some pointers, but it's still not going to change the work that I do. I want it rounded to the nearest 100, and anyway, basically traversal is what we're interested in for linked lists. So I have to walk from the head of the list to location 800. That is 800 of these fundamental operations rounded to the nearest 100. Again, I don't really care about off by 1 errors, which is why we're rounding it off to the nearest 100. I just want you to understand basically how much work you're going to do. Is that any questions on that? Yeah.
C, would it be 100 or 0?
Well, that's a good question. All right, so let's start with B. Remove 700 on the doubly linked list. Okay, well, similar, but now we have arrows going in both directions. And if you recall, let's say this is 700. So when I get to that location, I have to do some constant number of operations, which we don't really care about. What I care about is, what I care about is how long it takes me to get there. And then once I get there, I can remove that location. But of course, this is what? Yeah. Yeah, so we're going to walk backwards. So on a doubly linked list, we check to see where we are in the list. If we're in the first half, then we start at the beginning. If we're in the second half, then we start at the back. So we're going to start at the back here, walk from 999 back to 700, which is about 300. So the answer here would be 300. Okay, and you don't have to show your work, just write the numbers. All right, questions? Calling get 100 on an array stack. So this is an array-based data structure. So I put this line here means we cannot grow in this direction. We can only grow in this. So this is 0, 1000, and I want to get the element at location 100. Yeah, anyone? Yep. 0. Yeah, that's going to be 0, right? Round it off to the nearest 100. Yeah, we have to, whatever. We assign the value. We copy a value into a variable and return it, but we don't have to copy. We don't have to move a bunch of data, and we don't have to traverse some nodes. What will the 10th question be about? It'll be the same stuff. I think I just had, so the first 3 are sort of simple, right? But then we start to get into array decks and dual array decks and well, there's a bunch of different things we can do with a dual array deck and space efficient lists. So yeah, anyway, it's just, I try to give you the full complement. Back up, how far? Here? And then I guess to answer the other question, no. It will be on the array deck. So the question is, for the coding question, the example I give is an array deck, and the question is, will it be an array deck on the actual midterm? And the answer is yes. Okay, so understand how to program those functions on an array deck. Yeah. Okay. I mean, if you put 1, we'll give you the marks, but I'll have to remind the TAs to give you the marks though. So it's easier if you just put 0. So add 400 on an array deck. So how many operations is that? So again, we sort of have array deck. We have this pretend infinite array. And now I have location 400 where I'm going to insert the value x. But to do that, of course, I have to shift everything out of the way. And so in terms of fundamental operations, each one of those counts as a fundamental operation. So that will be 400.
Easy, bro.
Okay. Questions? All right. So now here we get a little bit fancy with dual array deck. We have a front size 0 to 400, and the back size is 600. So this goes from roughly 400 to 1000. I guess maybe call it 401 would be better. Even though this is actually 399 for being 100% accurate. And this is, but again, this is why we're rounding off to the nearest 100. I don't care about those off by one things. I care about that you understand the cost of doing these operations. Okay, so add 700. So I add 700, so how many fundamental operations is that going to require? 700 is over here somewhere. Yeah. We're adding at, yeah,
600 to 300. So 300, yes, 300 should be right.
exactly. So I would have to move 300 elements out of the way here. So the answer here is 300. Okay, and if that's because it happened to land in the back deck. If it landed in the front deck, of course, well, do I do that next? Yeah, so here we have we're gonna call, oh, set. Oh, never mind. So let's say I called add 300 on an array deck. Well, now 300 is over here. We want to add X, and again, we're going to, since we're on the front array deck, we're going to shift things in my diagram to the left, or to the left. So we're going to shift 300 elements this way. So in that case, this would also be 300. But here it can be, on an array deck, we look at whether we're closer to the front or the back. On a dual array deck, it really matters the size of the two stacks that we're using. Okay, questions? Yeah. The way that we defined a dual array deck is these are made of two stacks. Yeah. So I mean, that would be a different data structure. Not a bad idea, but not this data structure. Yeah. Calling set 300x on a dual array deck where front dot size is 600 and back dot size equals 400. How many fundamental operations is a set? 0, right? A set, well, I have, it's random access on an array-based data structure. This is an array-based data structure, even though I have under the hood, I have two stacks. But I just do a little bit of math. I figure out where this 300 thing is. It's in the first stack, which is sort of backwards. And then set is a O of 1 operation. But if we do remove on the dual array, the remove and add are similar, right? Basically, a remove at a location and an add at a location are going to be the same in terms of fundamental operations, right? Like there's an off by 1 error there, but again, I don't care about that. Yeah.
Remove and add the same for every data structure.
When you round to the nearest 100, in terms of, it's always the same sort of cost.
Yeah, like after you round it.
I mean, let's just say every sort of list-based data structure, I guess. But I would really qualify that. Everyone we've looked at, but I guess, I don't know every single data structure in the universe. But that is sort of the trend, right? So if I have to add and remove, it's sort of the same operations. I either, on an array-backed list, I have to copy. It's just a question of which way I have to copy things. And on a linked list, I have to walk there. So.
That I get.
Yeah. Again, we'll put an asterisk there, but yeah. Other questions? Okay. Yeah. All right. Add 700 on a space of, okay, so here's now, the last couple of questions are going to be challenging, right? So one is space efficient list. Oh boy, so this is basically a blocked list. The block size is 400, and these are made of array decks. Both the space efficient list and the blocked list or sort of block-based data structures using array decks. The difference is the space-efficient list is based on a linked list, doubly linked list.
पोएट्री लिखते हैं, गाने बनाते हैं।
And
पापा,
sorry, 1 second.
मैं मुंबई में एक बहुत बड़े टेक फेस्ट पे आई हूँ।
All right. So each of the blocks, this is 400 elements in the first block, 400 elements in the second block, and the last block would have 200 elements. Is that how we did it? Yeah. No, this is a, sorry, space-efficient list is a singly linked list. Is that right? What is this? Did we do doubly? No, it was a doubly linked list, eh? Right. Yeah. Okay, well, whatever. It's a doubly linked list. So if we call add 700, well, in this case, 700 would be roughly here. So to walk there is cost 0, right? We take one step, we're in the right block. To add at location 700 on a array deck, well, this is actually location, if we translate it, it would be location 300 on this array deck of size 400. Okay. So in this case, we would have to, we would insert it into the array deck at location 300. That would be 100 fundamental operations. Now there's a bunch of little stuff that happens as a result of that. Perhaps we bump an element into the next block. But of course, that is cost 1, which rounded to the nearest 100 is 0, right? So in this case, the bulk of the work is going to be done from adding at location 300 in an array deck of size 400. Okay. Now, the way I asked it here, the bulk of the work is being done by the array deck, but I could also, sort of invert this structure and give you a really small block size, where now you have to walk through, and that's going to be the thing that costs the most, right? So if the block size is 10, then I have 100 blocks. And if I have to walk all the way to the back, if I have to shift something to the last block, that's going to take 100 fundamental operations. So these ones are a little bit trickier, especially the space-efficient list. Questions? Yeah.
You're creating a space to add an element and you are removing last and then adding first. You calculate it as 1 operation or as 2. When you remove last and then add first, is it 1 operation or 2?
Yeah, it's like you could say either's fine. Yeah, no, actually, that's a good question. We're copying one piece of data, so we'd say 1. Yeah.
Well, yeah, you just decrease size of the end, so.
Yeah.
But well.
Yeah. No, so the way we defined it is that if we copy one data element, that's 1 fundamental operation. So anytime we have to shift from one block to another, that's 1 fundamental operation, not 2. But yeah, that's a good question because that could, sort of seem ambiguous. Yeah.
For the data structure we'll use for the block size, does it have to have a remove last of all one, like an array deck?
It doesn't have to, but that's the way we defined them, right? That's the way we built them with array decks. It sort of makes everything simpler. If you're going to be bumping things from one block to another. Yeah, so in both the space-efficient list and the blocked list, the inner blocks are composed of array decks to make shifting things simpler. Yeah, the spread. Well, in this case, there's no spread, right? Block size is 400. Ooh, yeah. Well, I forget the actual parameters of the question I asked you. I would assume, I pretty sure I thought of that. So I'm pretty sure it's going to be clear, right? So in this case, you would not do a spread operation. But yeah, I'll double check that, and I'll make sure that it's clear on test day. In this case, for this example, it's pretty clear. You would not ever do a spread or a gather because you have, you're going to take 2 steps, and the rule is if you take more than B steps, well, then you might have to do a spread or a gather. Which formula for the space efficient list? You shouldn't be really, if you just can't, you should not be blindly applying the big O notation here, right? You should be thinking about how these things, because the big O is just it's a worst case. And so I'm trying to sort of actually, that's why the rules are very clear. Don't give me big O, because big O is just, you memorize it. I want to see if you understand it.
That's one step to block 1, block with index 1, it was 1 step. Then remove last at first, you calculated it at 1 step together to create that space, and then you shifted 99 remaining elements, so total 101, which you rounded to 100.
Exactly. Yeah, that's it. So yeah, and sort of, what you want to sort of, or one of the things that's testing you on is like, where is the work being done? Like, what is the expensive operations that we're doing here? If I had a smaller block size, then traversing the list might take more operations. But in this case, like whether I have to traverse the list from front to back or back to front or shift, like those are all kind of trivial compared to the cost of adding to my array deck. So that's sort of that's the idea behind these questions, is sort of to test that I don't want to call it intuition because it's not intuition, but like mechanical understanding of these things. Yeah, exactly. Again, big O it's an upper bound, right? Big O is sort of worst case. So if I, in general, when I do these operations, if I'm not being specific, what's the worst case? But here I'm giving you a specific operation and asking you how much work's going to be done. So it is, yeah, don't rely on big O for this, eh? Big O can help you understand it, but I'm looking for something deeper. Yeah.
That's the number for a get of a linked list, like from the middle of a linked list. Do I like count it as n over 2 or like like 0? Like
From the middle?
yeah, like for example, we have a linked list to the size of 1,000, and we're asked to get from the middle.
From 500?
Yeah, so do I like write 500 or 0?
How would you get, I'm not sure why,
Like a get function.
but for a get function, the cost is in walking there, right? So get and set on a linked list actually are costly.
500 instead of like 0.
It's 500. Yeah, it's definitely 500 the way it's defined here. Yeah. Yeah, don't put 0. 0, get and set 0, basically any array backed, well, except for the, these sort of blocked lists are different, but I'm pretty sure I calculated correctly, right? So this is location, if I look at the far right, it's location 799, but it's roughly location 800. And so I'm inserting at 700 and I can shift 100 things to make room. Does that make sense? And then to shift, it cost me 1 thing to bump something into the next block. No, because these are array decks, so I can just add it to the front. and it's O of 1. Yeah. Yeah, these ones are going to be a little tricky. You'll have to think about. The first 8 should be kind of straightforward. Yes. Yes, the space-efficient linked list in particular is a mix of a linked list and array decks. So yes, if I happen to have to walk 100 over 100 blocks, then that is 100 fundamental operations. So yeah, there is, in this case, the runtime is dominated by inserting into the array deck, but it could be, if the blocks are smaller, that the runtime becomes dominated by the cost of traversing the list. Let's see. Other questions? Okay. So block list is similar from assignment 2, but this is, I mean, block. I should have named it a block stack, but it is sort of an array stack with blocks. So let's say I add 100 on a blocked list with a block size 200. Actually, this is not so bad. This is pretty straightforward. But again, so in this case, you know, no matter how many things I have to bump, that's at most 5 operations. Okay, so what dominates the runtime here is not going to be how, you know, shifting the elements over. It's going to be inserting. And this is, again, an array deck. So if I want to add this at 100 on an array deck of size 200, well then, you know, I'm shifting to the front or to the back, but either way, it's going to be rounded off 100 fundamental operations here. And I don't care about, you know, adding or removing a block. Does that make sense? Yeah. Yes, because these are array decks, right? Yeah. Yeah. That's, yeah. I mean, the midterm's already off to the printer, but if I had access to it, I would put a reminder here that these both use array decks internally. Right? That is very important to know. Other questions? Now the block list is different because it's a stack of, so get and set are gonna be kind of fast, right? I don't, for a get and set operation on a blocked list, I'm just doing math. I don't have to move anything. I don't have to traverse anything. I just have to compute the block and then compute the index, right? I mean, depending on how you implemented it, I think you can get away with like a slower implementation on the assignment, but ideally that would be a O of 1 operation. Yeah, adding a block would not count as an operation. Yeah. Questions? All right. So yeah, I have to put, some of them have to be tricky, you know. That's sort of it's a rule. Just work on the remove 600 on the, are you talking about the last question? So yeah, again, because of the block size, any operation is going to be dominated by the deck operations. So what did you say? Remove, you would have to figure out the block and then figure out, remove 600. Well, this is 200, 400, 600 would be, well, it wouldn't be here, it'd be here. But it's at the very front of an array deck, or, you know, the back of another array deck, depending on how you want to count. But either way, that's going to be an O of 1 operation, right? Array decks are very fast to add or remove from the front. So it's O of 1 time. Technically, it would be here, and it would take O of 1, and then maybe I bump this, and that would be 1 fundamental operation. So round it off, that would be, again, a 0. Yeah. So yeah, the whole idea is to know what is causing the work here. What is, where is the slowdown happening on these data structures? All right. the array deck. So yeah, I ask you to implement any of the methods. I'll give you a hint. It's going to be add front, remove front, add back, remove back. That's it. All right. We're going to do, we can do the fancier remove I because it sort of encompasses everything. But I'm not going to ask you to do that. But let's just think about what we would have to consider. I'm going to all right, well, the first thing always bounds check if I less than 0 or I greater than or equal to n, then, you know, exception. And yeah, I don't, again, I don't mind if you use a little bit of shorthand as long as it's clear what you're doing, but don't use shorthand here. This, I want to see what your bounds are. I mean, that's awesome. But I mean, that is a way to, first of all, it's a way to do very well on the midterm. But second of all, you probably learn things along the way. It's a very good. Anyway, now when I remove something from an array deck, again, I'm going to, well, I have to shift some stuff, but depending on, well, actually, the first thing I want to do is return it. So let's say t temp equals, and it's a. And I want the index of I, but it's not that simple on an array deck, right? It's actually, if you recall how this is implemented, j is the index of the front element. So in some sense, j is like your 0. So j is the first. So the index of the ith thing is j plus I. Okay. Of course, if we're on an array deck now, I start at location j here, and I add I elements. It's possible that, you know, I end up somewhere over here, j plus I. Of course, j plus I does not, you know, resolve to that number, so I have to do modulus a dot length. All right, so that's the element that I want to remove, and I'm going to return it at the end. Questions? Okay. What's that? Sorry? Or after what? Sorry? Yeah, I mean, technically, yeah. Yeah. So technically it's this. I would accept, you know, we'll be, we're not going to be super strict about stuff like that, right? So if you write this, first of all, neatness counts, right? So don't torture your TAs. Try and make it neat, and if you have to like leave out, you know, if that means no semicolons, that's great, right? If it makes everything look neater. Yes, add first, remove first, add last. No, yeah, it's going to be simpler than this. And yeah, I'm not penalizing for minor syntax errors, but like be careful, right? Because it is important that I get all of this information. Maybe, you know, it's not arbitrary, but I don't want you to make a mistake on the things that are important versus the things that are not important. So when in doubt, include it. But we're not, you know, I'm looking that you understand this stuff. I'm not looking to penalize minor syntax errors. Well, technically, yes, you're right. It's called array here. If you say a, that's fine. I get it, because a is what we put in the textbook and in the notes. So yeah, minor stuff like that. Yeah, I'm going to use a just to keep things neat. Although array would not be, it wouldn't be a bad idea because it's a little more clear. All right, other questions before we, yeah. Do we have to calculate J? No, well, we keep track of J as we go, right? So J is initially not shown here, but J is initially set to 0, right? And then if I add things to the front, it's gonna move. Or if I remove things from the front, it's gonna move. So yeah. You don't have to compute J, you do have to know how it is, I guess, over time, how it changes and how you use it. All right, so yeah. If n is less, or sorry, I is less than n over 2, then we're going to shift. This means we're closer to the front, so we want to shift things. We want to close the gap from the front, which means in some sense I have the thing that I want to remove, and I want to, well, again, I'm not asking you to do this, but for future reference, right? Because this makes a good multiple choice question where I just say, well, which one of these 4 loops sort of closes the gap on a remove. And so I would start at the index and walk towards 0 or J. Right, so my 4 K equals I. K is greater than J, but J, no, sorry. K equals I, K is greater than 0, K minus minus. And yeah, I think that's even correct. So I would often make an off by 1 error there and say like greater than or equal to 0 or something. But this seems to be correct according to my notes. And then I want to copy things from the larger location to the smaller location. Or sorry, from the smaller location to the larger location. So I would say A at, now instead of I have K plus J mod A dot length equals A. And now I said what? Yeah, is it K? Yeah, it's K minus 1. Yes, you're right. Thank you. K plus J minus 1, or K minus 1, I guess, would be. See, this is why I'm not asking you to do this. This is the type of thing when you sit down to code it, you think very carefully about it, you get it working, and then you never look at it again, and just hope that it stays working forever. So this will shift things, and then, well, as a consequence, of course, I shifted everything over by 1. J was initially here, but now the first element is going to be here. All right, so that means I have to increment the value of J and decrement the value of N, and then I think that's it. The one thing, I will spare you the else, but the one thing we have to remember is to check for resize. So if N, or sorry, A dot length is greater than 3 times N, right? Yeah. In this case, I would want to resize. And again, this is if you put less than or equal or greater than or equal to, that's fine, right? Asymptotically, it's not going to make a difference. This is what we're looking for, though. Okay, and yeah, I think that's it. Again, I'm not going to ask you to do, so you won't have to do this part. But you will have to think about if I'm removing or adding to the front, what do I do with this j variable? And if I'm adding and removing to the back, well, actually, you don't have to do anything to the j variable, right? Yeah, array.length then. Okay, sorry. I will. All right, yeah, good stuff.
Maybe we should have it modular, j plus one.
Yes.
Because in case j is at the last element of A, of the array
You are
A, then it will go off, who knows, so.
you are absolutely correct. So j equals j modulus a dot length. So I might go off the end of the array, and then n minus minus. So I did forget something. All right, so things you need to remember, how to compute an index, what to do with j, and the modulus. Remember to increment or decrement n, and remember to check for a resize. If it's a remove, it's going to look like this. If it's an add, it's going to be if a dot length less than, well, actually, it's like for an add, you want to check because it's okay for it to be full. So on an add, you would do a check up here somewhere, and you would say, well, if n plus 1 is greater than a dot length, then I need to resize, right? So if n plus 1 is greater than a dot length, then I will call resize here before I add anything, so that I have enough room. Okay. All right, so yeah, take a look at I can't remember, I think the notes have the add front, remove front, and add back, remove back, but if not, you should be able to recreate it. Somebody asked about the calculating the modulus, right? So I'll quickly go over a small example. So this is 0, 1, 2, 3, 4, 5, 6, 7. So there's 8 locations here. And let's say that j is currently pointing to 3, right? And there's data in here, B, C, D, E, F, G. So when I call get, what is it, 6 or 7? 7 is the last one, so 6, right? So if I call get 6, what do I have to do? Well, I actually, the way it's numbered, or the way I wish it was numbered, is 0, 1, 2, 3, 4, 5, 6. So I'm asking for element G. So I have to convert from this numbering to this numbering, right? And so you can kind of do it it's easy to do like a sanity check. Well, I want element 6. This is 0, 1, 2, 3, 4, 5, 6. So I know I want to return G. So whatever my, whatever my formula is should give me back, well, it should give me back 1, right? It should give me back the index that contains G. So if I said, well, this is, I is equal to 6. So I say A, and sorry, J is equal to 3. So A at J plus I, well, if I just left it at that, then I have A at 9, which is off the end of the array, right? So J plus I does not give me the correct location, but if I mod by A dot length, well, then this is A of 3 plus 6 mod 8. And that is actually, if you do the math, that's 9 mod 8, which is equal to 1. And that just happens to be where G is. So yeah, you can do little sanity checks like that to make sure that you know, it's a good way to make sure that you're kind of, you know, not doing any sort of obvious error. All right. Yeah. Also acceptable instead of the, well, if else. Yeah, you could do something like if I did J plus plus, I can say if J is well, equal to A dot length, then J minus equals A, or, you know, J equals 0. That would be probably the easiest way to write it. Yeah, you're free to do that instead of modulus, right? As long as, you know, obviously, I would actually even like encourage that. If you understand how to do these things, then that's great. This really demonstrates that you understand it. Of course, it's also okay to kind of memorize what you're supposed to do. All right, questions? Okay, root array stack. All right, so let's draw in the quick root array stack. So I have a list of blocks, and each block is size 1 larger than the previous block. And they're all indexed. So here I would have this as index 0, and 1, 2, 3, 4, 5. Of course, each of those is an array that has its own index. So for example, on this one, it's 0, 1, 2. So again, I have to convert. I say get the thing at location 5, and I have to convert that to an index of a block. So 0, 1, 2. So if I said get 5, well, in there, I have to figure out that B is equal to 2. That's my block. And the index into the block is equal to 2 as well in this case, right? So let's say get 4. So get 4, that'll give me J equals 1. So that's this guy here. All right, so if I have a very small root array stack, I can eyeball it. So we're giving you a very large root array stack and these formulas that you can use. All right, but everybody understand what a root array stack is? Okay, so how do we do it? Guess and check. Nope, guess and check is perfectly valid. In fact, that's what I'm going to use right now. So I want to compute the block first of all, and to compute the block, we use this. So why we use this particular formula is explained in the notes. I'm not going to go into great detail on it, but of course it, you know, this is I equals 1 to B of I. That's B plus 1 over 2, which is basically, that's the sum. If I sum up B blocks, all of their locations, that's what that is. Okay, and then, but of course, this one's a little bit different because the indexing starts at 0. So we have to add 1 to B and add 1 to I in order to get that to work. But regardless, I give you the formula, so you don't have to understand it. You have to understand how to use it. So I'm going to say get, what is the location in terms of the block and the index into the block if I want something at index 746. Okay, so I'm going to erase all this stuff here, and at least, and just so that we only have the sort of work related to this question. But yeah, so we're going to do this one first. I'm going to rewrite it over here. B plus 1, B plus 2 over 2 is at least, is it greater than or equal to? Yeah. I plus 1, and we want the smallest B that makes this true. This true for I equal to 746, right? That's this number here. And yeah, so guess and check. So, well, the first thing I'm going to do is say, well, this is greater than or equal to 747, right? So I plus 1 is 747. So let's plug some values in for B. Let's say that I did, what's an easy one? What's that? Yes, I'll go into that after, because this is sort of easier, and you'll still get full marks for it.
The quadratic equation, so
Yes, it is. Yes. You can also use the quadratic equation, right? It is faster if you know it, yes. I'm going to use the guess and check here. Is it okay if we use another formula because there's diffs? Yeah, just, I mean, explain yourself, right? The TAs have to mark this and make sure that you're not just writing down. I'm not sure what other formula you mean, but there is the quadratic formula, right? So you can change this. Yeah, well, that's essentially what we're doing. It depends on what you mean by solve the inequality. But yes, you can solve this using the quadratic equation, right? What's that? Yeah. Yes, yes. You take the ceiling of the quadratic equation. So that's in the notes. I'm going to do guess and check, and then we'll talk about the quadratic equation after, okay? So guess and check, I would just take, so let's say B equals 9. And then if I fill in B, well, that's 40 times 41 over 2, which is 20 times 41, which is 820. So that is greater than 747, but is it the least number that's greater than 747? Perhaps not. So let's guess at 38. So 38 gives us 39 times 40 over 2, which is 39 times 20, which is what, 780? Which is still greater than or equal to 747. But it looks like if I go down one more, that's probably less than. So B equals 37. I get 38 times 39 over 2, which is 19 times 39, which is what? I think it's 741 if I'm not. I don't have a calculator, but I did write it down. Yeah. So that's 741, which is actually less than 747, right? So the smallest value, integer value for B, that is still gives me B plus 1 times B plus 2 over 2 is still greater than or equal to I plus 1. Well, in this case, that is B equal to 38. Make sense? Questions? Okay, so I have my B value. Oh, this is, I should have given you, well, there's extra pages at the end if you run out of space. So B equals 38. So now how do I calculate my I value, or my J value, sorry? Well, I want to basically subtract this from my I value, right? So this is every single location. The sum of all of the locations and all of the blocks previous to the block that my element is in. And if I just take that value, which actually I just so happen to have, right? It's this one. If B is equal to 38, and then I take b times b plus 1, well, that's actually 38 times 39 over 2. So it's 741. So guess and check kind of, whatever. I mean, you can use a quadratic equation as well, but guess and check's not a bad way to do it. It will give you full marks. Also, guess and check if you don't have a calculator. If you forget your calculator, guess and check still works, right? Whereas a quadratic equation, you might have some trouble with that square root. All right, so then to get my j is I minus b times b plus 1 over 2, which is 700. Now, carefully here, because I is 746, not 747. So 746 minus 741, is it 5? Is that right? That should be right, unless I made a dumb error there. So yeah, do be careful, double check your work, but just showing the work will, that'll give you some marks. If I can see that you know how to do it, that will give you some marks for sure, even if you make a math error somewhere. Yeah, so b equals minus 3. So this is the actual equation. Yeah, that's good. I'm going to copy this. So if you have a calculator in particular, we did this in class. Will this paste here? Maybe I need a... Yeah. So that's the equation. So you're also free to use that. You can memorize it or you can derive it. But given I and a calculator, because again, the square root's might give you a bit of trouble here. But if you have a calculator, then you can compute b. Just make sure you write down, the function that you're using. Yes. Yes, this will be the same question on the midterm with different numbers. So yeah, this procedure, memorize. If you memorize this equation, you're off to a really good start, and you have your calculator, right? Then you just write down the equation, plug in your I value, and you can get back b. And then you still have to do this part, but that should be okay. Oh, what happened here? All right, questions? Okay. Skip list, I mean, there's a fine line between too easy and too hard here, and I feel like this is kind of an easy question. This is a skip list, so a couple things to denote. I should have said that it was a set, but I did say store these characters in alphabetical order, right? So a sorted set. Each element is added in L0, so these are the sort of computer-generated sequences of heads and tails. And well, this is actually pretty easy. First of all, they're going to go in sorted order. So A, B, C, D, F, right? Starting here, A, B, C, D, F. I can kind of cheat, even though I gave them to you out of order. All this trickery. B has 2 heads, so it has a height, whoops, here, height of 2. C has just tails, so that is height of 0. A has 3 heads, so that has a height of 3. And what is it? F has 2 heads, so that is a height of 2. D is nothing. Is that it? C and D are both tails. Yeah. All right. And so then I should also draw in my sentinel. And then fill in the, or you can say they're implied, whatever. Okay, so that's my my skip list. Should be easy. You get a couple easy marks there. Now we're going to add E to the skip list with a node of height 2, and that's going to require a find operation. So we have to basically describe the find operation. What steps do we have to take? So what steps do we have to take? So we want to, we're adding E. And so we want to do a find of E. So we start here at the highest point on the sentinel, and we're going to take, I'm just going to draw in the path, and then I will translate it into the question on the next page. From A, I look, this points to null, so I'm going to take a step down. And then I say, well, the thing I'm looking for is B less than the thing I'm looking for. So the answer is yes. So I go over here. And then this is pointing to here. And is F less than the thing I'm looking for? The answer is no. So I'm actually going to go down again. And then I'm going to say, well, is F less than the thing I'm looking for? The answer is no. So I'm going to go down one more time. And then I'm going to walk to D, which is, and then I'm done. Right? That's the predecessor node. So the find operation stops at the predecessor of the thing we're trying to find. Okay, so when I write that in, what do I say? So I start in L3 in this case, and I go from the sentinel to A. So sentinel. What's the correct way to spell sentinel? It's E. Okay, so in L3, I take one step across, and then I step down from L3 to L2 in A. And then the next step is here from in L2 from A to B. And then the next step, 2 steps down in node B. So B from L2 to L1, and B from L1 to L0. And then in L0, we would just go from B to C and then C to D. Okay, so that's the path on a call to add E, which requires a find operation. Will you specify in the midterm like find in the node and so on? The midterm question is exactly this, but with different, you know, with different characters. It's slightly different. Again, you know, if you study and prepare, I'm giving you basically all the tools, hopefully all the tools. If you just put in the time to study, you should do very well. But yeah, so this is there anything not clear about this? Okay, so that's it. And then to insert E, the node E must be added to multiple lists. So E was added with a height of 2. Well, you don't have a lot of room here, eh? But, so I'm going to put in mini E with a height of 2. And so which lists is it inserted into? Well, it's inserted into L0 between D and F. And L1 between B and F, right? And then L2, I think also B and F, yeah. Okay, and I think I said here for full marks, list them in the order they would occur in the skip list code from the ODS library. Don't worry about that. Because that's arbitrary, right? So you don't get, there's no advantage. You save it on a stack and then you execute you insert it in the list in the stack, but whether you go from the top to the bottom or the bottom to the top, there's no advantage to doing one over the other. So I'm going to, it will say this, don't worry about it. Just any order's fine. All right, questions? Okay. And yeah, that's it. Then you'll have 2 extra pages. You can do your rough work. If you put your answers here, please mark it very, very clearly, see, so the TAs can find it. And, you know, try to write neatly as much as possible. So yeah, that should be it. Questions? Okay. I guess maybe we'll break a little early today, so rather than 1G, yeah, for sure. So the space efficient list, maybe we can try and mix it up a little bit. Are the solutions posted? Not really. I mean, I could, but there would, I mean, feel free to make up a solution and share it. I'm not sure. I'll make solutions if I have time, but I'm working on assignment 3 tomorrow. So depending on how long that takes to do, you know, I'll do this. I'll make solutions if I get around to it, but you know, feel free to share with each other on your Discord. So asked to do G again. So let's do something. I'm going to put a question that is actually more difficult than what I would ask you. So let's say we do something funky like the block size. Well, man, I really want to go back and look at what I did there because yeah, because it's a space efficient list. If I add something, it's not clear that anything will get bumped, right? And I'm almost certain I accounted for that. If not, I will make it clear on Thursday. But so there's really a limit to the kind of questions I can ask you, unless I tell you specifically. So let's just do B equals, did we say B equals 200? Okay, so so I can draw out my blocked list. Or we can do, okay, let's try a couple. I have 2 of them in mind, actually. Okay, and then I say add at 500x. So how many fundamental operations is that? Well, once again, we are dominated by the cost to the array deck. I can, to walk through this does not, you know, this is a round off, right? Even though maybe I walk 4 steps and maybe I bump something 4 places, those are all going to be rounded off. So I don't really care about those. But location 500, well, this is 0, 199, 200, 299, 300, or sorry, 399, 400, 599. So 500 is dead center here. So to walk to that block, 2 steps. To insert into that block, well, I have to move, well, whether I move 100 things this way or 100 things this way, both of those take 100 operations. So it's like the total number of fundamental operations is like 102, and then I'm not including the fact that something might get bumped. Let's look at another variation of this. Anybody questions on that? Okay, so here's a variation. Let's say I said block size equals 5, right? So there are 200 blocks. Okay, so I'm not going to draw them all in, but I'll draw the first couple, 0 to 4, 5 to 9, etc., all the way up to what is it? 995 to 999. Okay, and then let's say I call get well, what can we say? 400. Okay, so what is the what's the runtime of this? I mean, this one's a little bit trickier, but so actually I don't know that I would. This actually I think is fair game. It is a little bit tricky though, like the last couple questions are going to be tricky. Yeah, you kind of have to think, well, it's on a doubly linked list, and so I'm going to, well, I need to decide if I'm starting from here or from here, right? So I'm going to basically, I want to walk there. I want to walk to the proper block in my doubly linked list. What's that, sorry? Block 39, yeah. Or 78, yeah. Or whatever. Yeah, 79 or something. Right. So I'm going to walk, yeah. I'll have to walk 80 blocks essentially. So yeah, 400 is less than n over 2. N is equal to 1,000. So it is closer to the front. So I'm going to start at the front. And then every step I take, I skip at least 5 elements, give or take, right? So, you know, this is a blocked list. So there's some ambiguity here in terms of whether I'm at B minus 1 or B plus 1. But, you know, presumably, if I asked you something like this, I would tell you that each block has exactly B elements. And then you can sort of, you know, walk 80 blocks. That's 80 fundamental operations. And if I was rounding off to the nearest 100, it would be 100. Now that's a little mean, right? Maybe that might be slightly more complicated than I would ask you, but not by much. Yeah, questions? Okay. Yeah. Well, I'm counting to 400 and I'm skipping 5 each time, right? So 5 plus 5 plus 5 plus equals 400. And so how many of these do I have to do? Right? So every time I take a step in my doubly linked list, I skip 5 elements. Sorry, to 400. So it turns out that 5 times 80 is equal to 400. So it's 80 steps, right? If I have to go to location 400 and start at location 0 and I get to skip 5 each time, then it's 80 steps to get there. Question H. Well, question H is different, right? So blocked list, any get or set I can do in constant time because this is a list, linked list of array decks, right? So traversal is going to cost you. If I have to walk, that's going to cost me. This is an array stack of array decks. So similar to, well, similar to the, I guess, the root-ish array stack, I can, if it's just a get operation, I can compute in constant time. I can compute, you know, b equals, sorry. I'm just, I already used b as a variable. I didn't want to use it again, but so hopefully you get the idea, right? If I have to go to location 400 here, I can just say, well, I take the block size, which is 200, and divide my location by the block size, you know, integer division, and I get the index of the block. You don't have to know all that. You just have to understand that you can do it. You can jump immediately to the correct block, and from there immediately to the correct index. So a get or set is O of 1 on your blocked list. As long as you've implemented it correctly. You know, on your assignment, you may have gone away with something a little different, but that is fundamentally. So you don't count the operations of everything shifting after you add X. Depends on which one you're referring to. So on the, sorry, blocked list, this is really, so on the blocked list, if I do a get or set, that is a O of 1. It's not an add, right? But if I didn't add, yes, I would definitely count the shifting, right? So if I said add, if I did add 500x on my blocked list, then the only thing that cost me is the shifting. Everything else is sort of kind of negligible. I might have to bump a couple things, but there's just a couple it would still round off. Yeah.
So size 5, and there were 200 blocks of size 5. And we said we walked, it took 80 steps to get to 80 spots.
Yeah.
And then we put, it's possible that it also cost us then ring plastic at first, and there will be a lot of them because there's many blocks, and
Yes.
could cost us.
Yes, that could cost you, but I don't, I'm trying to remember the exact question I asked. I don't think I've been, if I'm that mean, that was a mistake, but I'm not trying to be that complicated. I want you to understand blocked list versus blocked array stack, right? But yeah, I'm trying not to, again, I'm not trying to trick anyone. I just want you to sort of, yes, but if I did add on the space efficient list, then there is the cost. And if I had block size 5, then of course I have to, yes, I might have to shift some stuff, but I would only shift B elements, eh? Yeah.
We still, like when we look at the code, we're only looking at the B blocks starting from this one and the next B minus 1 blocks. When we're looking for a free space, like for a space to insert, therefore we would be shifting to the right, even though we may be at the position 80, we would be still shifting 120 times probably. But because of that, not 120, we could just shift B equals, we would end up to be just spreading after 5 blocks.
Yeah, you would spread after 5 blocks, yeah. So assuming everything was full, yeah. Again.
Because we would go 5 blocks and then we would have spread operation and find a place to insert.
Right. Yeah. I really want to double check that now because I'm like, did I think of everything? But yeah, so we've went over every plausible scenario. If there's a problem on the test, you will know about it on test day. I don't think there is though. I just can't remember exactly what I asked you. Would it be one operation if you add 500x on which data structure? And what's the, so on a blocked list, if the blocks were size, that would cost 100, right? If the blocks were size, or what did I say? So in this example, we have a block size of 200. If the block size were 100, that would be one. Sorry, I don't really understand what you mean by one extra operation either. So if, let me get some free space here. So your question was about an add 500x. And so if the block size is 200 this is a blocked list. Then this is, 399 here. And my 500 element is here. And this is an array deck. And so I'm going to have to shift 100 elements. So the cost of this with b equal to 200 is the cost is 100. However, if I say, let's say 100. If I say b is equal to 100, then a call to add 500, well, this is 100, this is 100, so this is 99 here. This is 299, this is 399, and then I would have 499. And then the next one would start at 500. So that would be a zero cost operation, right? So even adding just to get there is fine. I mean, you would have to shift a couple, but it would round off to zero. Yeah. Other questions before we? All right, let's take a break. Let's come back at around 10 after 1, and then I will answer any more questions anybody thinks of about the midterm, but otherwise we will go on with. Okay, so 12 after 1. Anybody have further questions on the midterm? Okay, so I did confirm, I did look to make sure I didn't make any. I mean, I am the prince of stupid errors, but I made sure I didn't make any stupid errors. So nothing I ask you on the, especially for G and H here, the things that I ask you are no more complex than the things we went over, right? So I'm really not going to ask you to analyze things like spread or gather. Again, if I called add on this space efficient list, spread or gather would not come into the equation, right? Because I only spread or gather if I have to walk more than b blocks, which that's 400 in this case, and there's only 3 blocks. So this solution, I suppose I can, if I remember, I don't know if you can make sense of all this. I can definitely post this solution though. There is a lot of, you'd have to, there's a lot of messy stuff, I guess. But yeah, I can do that. Other questions? Okay, let's get back to hash tables. So yeah, let's quickly review what we've been talking about for hashing in general. This is called hashing with chaining, or I think there's another bucket hash or something like that. But essentially we have a table, and when I take some integer, let's get red here. When I take some integer x and I hash it, it's going to give me an index into this table. Okay, so that applies to any integer. And so what happens is, well, sometimes I get 2 things that hash to the same location, right? Because there's just if I want to store a very, data with a lot of variance, I'm inevitably not going to be able to find a perfect hash function. So I can get collisions. And so what I do in the case of a collision, well, in this case, I use hashing with chaining, which means that I just add a list at each location of my hash table. Okay, so the implications of that are, well, so in terms of performance, we assume that hashing is O of 1, right? So hash of x, it's just some math. This is a constant time operation, so very fast. I can very quickly find out where something is supposed to go. So if I want to, for instance, add X and then add Y, well, I would hash X and then I would add it to the list. And then I would hash Y and then I would add it to the list. And that's fine. Adding is going to be O of 1 because I'm not doing anything special. I'm just adding to the back of the list. Okay. So the real cost is if I call something like find X or remove X, well then these both rely on the hash function. That's fine. I can do that. But now the hash function returns a list. And so now I have to do find X or remove X on that list. Okay. And on an unordered list, find X and remove X both mean I have to do a linear search of the list. So this would be, not really a lot of space here, but O of list dot size. Okay, so hashing with chaining, it's a nice simple, as long as I have a hash function, this will all work. The question is, well, what is this really? And so this depends on a good hash function, and a good hash function is what we call has a good universality, or the universality of our hash function. And this is how much hash X spreads elements. Essentially, we want hash X to return a random number between 0 and some value that we care about, which is the size of our table. Okay, and that is called the universality, is basically how close to purely random this is. And so that is going to have an impact on the expected size of our lists. Now, we never know, right? We can get very unlucky and everything get hashed into the same location, and then everything becomes a list operation, find and remove on an unordered list, and it's going to be expensive. But with a good hash function, that's very unlikely to happen. Yeah. Okay, so that's where that's sort of a review of hashing with chaining. So that is the very most basic sort of hash table where we put everything into a list. And then we talked a little bit about this multiplicative hashing, and it looks very complicated, but sorry, any questions on this so far? So multiplicative hashing looks very complex, but it's sort of not as bad as you might think. So for example, all we're going to do is, assuming that we can take our integer x and we're going to multiply it times a random odd number z. Well, this gives us a number, and this number might be too big to fit into a memory location, so we're going to cut off the highest order bits, right? They're overflow, and if we don't explicitly track overflow, it just gets eliminated. So we get, for free, we get to sort of chop this into 8. If our word size is 8, right? And so we take our value x that we want to hash and a random odd number z equals 17. Well, 42 times 17 is 714, and we look at the bit representation. And in this case, we're assuming we're on an 8-bit machine, right? In reality, we're on a 64-bit machine most of the time, or if it's a bit older, maybe a 32-bit machine. But what happens is these just get lost. If I don't specify that I want to take care of them, they just get thrown away. So for free, I get this operation, this mod 2 to the power w. And then what I do is, well, then I have a random number that it's about the size, that's the same size as an int. I have some random integer, and I just, well, let's say that I had a table of dimension, well, I just take the highest order bits, as many as I need. So for example, if I had a table of size 4, then to index every element into that table, I need 2 bits, right? With 2 bits, I can index 0. This is 0, 0. This is 0, 1. This is 1, 0. And this is 1, 1. So for a table of size 4, I would take my random number, multiply it by the number that I want to hash. It's going to give me this number, and I just look at the highest 2 bits. So in this case, X would go into location 3. So that's it. That's it all looks very complicated, but it's sort of simple in practice. I take my number times a random number, and then I look at the highest bits, and I take as many as I need to index into my table. Okay, so that's multiplicative hashing. As I mentioned on a test, well, if we try to keep things a little bit simpler on a test, so maybe I'd give you a hash function of just like take your number and mod into the table, something like that, right? So anyway, I won't confuse the issue right now, but yes, D is equal to 2. So for these hash functions to work, right? So I'm returning some number of bits. Any number of bits gives me a number that is some power of 2. So yeah, so this is my table size is 2 to the power D. So one of the important considerations for this type of hash function, and for most hash functions, is that all of my tables are going to be some power. The size is going to be some power of D, or 2, sorry. Right, so it'll either be size 1, size 2, size 4, size 8, 16, 32, 64, and so on. And that way we get nice, when I take these bits, I have exactly the right number of bits in order to find an index into that table. All right, questions? Okay. Yep. So that's it. It's Z is an random odd number, yes. Yeah. And we talked about if Z was even, then we can really, if we get unlucky with Z, it can really mess up. Everything can be hashed into the same, all the same locations, or the more zeros at the end of the random number, the less universal our hash function is. We didn't really prove that, but we sort of talked about how that might happen. Okay. And then, yeah, so to do this hash code on Java, it's very simple. It's Z times the hash code of whatever object. Typically, you should, well, I think, I think it used to be that Java returned the memory location, but they don't do that. I highly doubt they do that for most of the objects. Say in a standard library, they would give a more sensible hash code. But regardless, hash code is just a number you can use in your hash function. It takes an object and gives you back a number. And then I just I shift it right. I shift the bits right that many, and that gives me the D highest order bits of that number, as we talked about. Okay. And yeah, this is again, I think we stopped roughly here. This is an example with a more realistic example where the word length is 32 bits. I don't think it's any easier to understand though, although you can take a look at it if you like. But yeah, it does the same thing, right? I'm cutting off these numbers here. Those are overflow. And then I want to div by this 2 to the power W minus D, and I get the D highest order bits. Anyway. All right, so all as mentioned, so that's the hashing with chaining, and we talked a little bit about that hash function. Now we're going to prove, not again, we're going to use very sort of a loose, and in this case, actually, the real proof of universality of hashing is brutal. I don't even understand everything about it. So I'm not going to do it, but I'm going to do what I sort of gleaned from it. So our perfect hash function, right? So if A is an event that's two basically random elements that are not equal, the probability that they get the same hash number is 1 over the length of the table. And that is that is universality of your hash function. That's a perfectly universal hash function, right? That's what we want. Basically, it's just scattered completely randomly. So for us, multiplicative hashing is what's called near universal because it clusters up a little bit. It's not perfect. So you are going to get a few more things than you would like hashed to the same location, but we're going to prove that it's really not too bad. All right. So the first thing we're going to do is we're going to show this later, but I'm not really going to show it. That is the really nasty proof. So just I'll kind of give you the idea behind it, but right now we're going to just assume multiplicative hashing gives us this probability of a collision, okay? Which is twice what perfect hashing is, but it's still pretty good. And so what we're going to show here is that basically I would expect, well, when I call hash x, it gives me this location, let's say, and let's say my hash table was full, right? So I have n elements and n is exactly the size of the table. Then on average, I would expect to have 2 extra elements hashed to that location in addition to my x, right? Which means that basically this find x and remove x, they have to search this list on average. But even doing a linear search, I have to look at 3 different locations. So we would say that they are O of 1 expected time. And that means I really expect them to run very, very quickly. Okay. A little bit of math. So our probability that 2 random elements hash to the same location is 2 over the length of our table. And so again, this is, yeah. I mean, I really, it's difficult to make a good curriculum where, you know, all the required prerequisites are met at the proper time. It's a hard problem. And so I'm using sort of math that you are not required to know, just hopefully to give you a better idea. So yeah, try and absorb the ideas behind it, but how you would compute it is I would use what's called a random variable, which basically is going to count the number of times there is a collision. And specifically, it's going to count the number of times there's a collision with my value x. All right, so the nice thing about expected values with indicator random variables is they're equal to their probability. And so if I compute the number of elements, this is y is the number of elements that are in my location with x. And so I look at the, you know, basically the probability that each of those elements gets hashed to the same location as x. And that is my 2 over the length. And then, well, all of the elements that are not x are n minus 1. And I get essentially less than 2 other elements, right? So basically, if I don't count x, then I would expect 2 other elements to be in this location on a full table. So even on a full table, this is going to perform pretty well. And yeah, I don't know. I am torn about what to do with all the math in this course. I think it is useful, and in computer science, the science in computer science is like we are putting guarantees on performance, and we're using math to do it. So I do think it's important, but yeah, I don't know. It means that I teach you this stuff, and maybe you don't know. Maybe you really don't have the proper frame of reference to understand it. But yeah, anyway, questions? Okay. What's that? NX? Well, assuming this is a set, right? This is the simplest case. But you're right. If we allowed multiple, if we allowed, storing copies of X, then NX would be greater than 1. So it's sort of, this covers both. Make sense? Sort of. All right, so the theorem chained hash table implements the unsorted set interface, where all of these add, remove, and find. Well, add is O of 1, but find and remove are O of 1 expected time per operation, because those lists are going to be are pretty short. Furthermore, of course, we can amortize all of the costs, all of the calls to grow, like once the table fills up. Once we have n elements and n is at least the size of the table, then we grow the table so that there's not too many collisions. And we already know how to do that. Near universality of hashing. So again, I'm going to briefly show this and then we'll move on. But if I have two numbers, x and y, and they're hashing to the same number, well, then what I'm going to do, well, I apply the hash function. That means that this set of numbers is equal to this set of numbers in some sense. And so, again, there's a lot to this proof that I'm not showing you, but as it turns out, if I subtract x and y, right, I just see, I take the absolute value of the difference, I multiply that by z, then these 4 bits, it turns out, can be 1, 1, 1 or 0, 0, 0. And so I have d bits, and so 2 to the power d possible outcomes, and out of 2 of them result in a collision. So that's where we get this probability from. Anyway, questions? All right, let's move on. Okay, so let's see. Actually, I think I have a woo clap. Yeah, all right. I think these are good, not too complicated. So yeah, just 3 quick questions on some of the stuff we took. Very little math, I promise. All right. So assume we make a hash table of student, the student information, and there's 1,000 locations in our table. And then we're going to make a hash function based off the student numbers. Right, so the student numbers are a 9-digit number. And they're given out in numerical order, right? So if your student number is larger than someone else's, that's because they were a student before you were a student. So yeah, which of these 3 numbers, the first 3, the middle 3, or the last 3, would give you the best hash function, right? So which means that we want a hash function that is as random as possible. See what's So in real time. So anybody know the first 3 digits of their student number? I do. I know all the first 3 digits of all your student numbers, except for maybe a couple, is 101, right? So if we use a hash function based off the first 3 numbers, you guys would all hash into the same place. So yeah, that's not very good. The middle 3 might be slightly better, but so we want numbers out of that that have the highest variance, which means that they're least likely to be the same. And out of those, the last 3 numbers are going to be the most sort of chaotic, right? The first 3 numbers rarely change, right? Like you guys are 101, I'm 100, and I came here way before you guys, right? So yeah, those numbers don't change very much, but the last 3 numbers change all the time. So yeah, if we're trying to choose, you know, a set of 3 numbers from our student number that have that are sort of the most chaotic in value, that would be the last 3. Right, questions? Okay. What is the universality of a hash function? I mean, we did talk about that. So yeah, what do we mean by that? All right, well, that's good. Most people paying attention? Yeah, we did just talk about that, but I know how easy it is to tune out. You should try if you go to a conference ever and you listen to the talks, some of them are really great, but others are so detailed and it's like, you know, you're watching, you're paying very close attention, and then my mind drifts for like 1 minute and I come back, I'm like, I'm completely lost. I have no idea what's going on anymore. So yeah, I do sympathize. I mean, I don't, no judgment for, you know, when something we just talked about, you missed it, I get what happens. But yes, how well it spreads out the values. The universality is basically how much randomness your hash function gives you. Okay. Java objects have a function called hash code that returns an int. We can then use this int and hash function to determine where in the table to store this. Hash code used to return the memory location of the object by default. Maybe it still does. Would this make a good hash code? Why or why not? So hash code is the number that you feed into the hash function, right? So we have objects that might be strings or students or whatever. So I need some sort of numerical representation to use in my hash function. So memory address is one idea. So why or why not would this be a good hash code? Yeah, okay. Well, let's talk about, I mean, number 2, yes, because no 2 objects will ever be at the same memory address. That is true. No 2 objects will ever be at the same memory address. The problem with that is, so basically 2 objects will have, you know, we know we're not going to get too many collisions. The problem that might arise is number 4. What happens if I have 2 copies? I'm hashing students maybe, and I have 2 copies of a student. And so when I say I have a copy of the student in my hash table, and then I have another copy, and I say, well, tell me if this student exists in the hash table. But this copy is at a different memory address. And so might hash to a different location. So actually, number 4, like that's kind of a big problem. You really don't want, if you're going to do hashing, you have to be careful what this hash code returns. I highly doubt for Java string that it does anything like that anymore, but you never know. Does that make sense? Questions? Right. I might have two objects, they're different objects, but they might be equal and they should hash to the same location. All right. Okay, so that is hashing with chaining. We're going to talk about a different form of hashing called linear probing. I do like this, and perhaps you guys can relate after doing assignment 2, is that when you're coding, especially with data structures, you have to be perfect. It has to be error-free. Sure. Yep. So yeah, this is perhaps something that you guys have just experienced, or maybe you found it easy, in which case, good for you. So linear probing is also known as open addressing, and the idea is that, well, I'm not going to store any lists at my locations in the table. I'm just going to store data. So my table, again, it's an array. But I'm going to hash something, and then when I hash it, I'm going to get back a memory location, and maybe that memory location is full, or maybe it's empty. And if it's empty, I can just put the thing there. And if it's full, I have to look for an empty location that's not too far away. So each location stores at most one value. And ideally, I hash X and it gets stored at the correct location. But of course, it's a hash table. The hash function might not be perfect. So it could be that I hash X and Y to the same location, right? So I've called add X. Let's call these X1 and X2, assuming these are a set. And then I call add Y, and I hash Y, and when I look at this location, I see X. Well, what I'm going to do is I'm going to say, well, let's look right next door. And then I'm going to say, well, actually, there's something there as well. So I'm going to look next to this one, and then I'm going to say, oh, there's space here. So I'm going to put Y there. So that's basically the strategy, right? So I have a table. It's going to be, I mean, we have to make it kind of big. But as a result, when I hash, probably I'm going to have an empty location. But if I don't, I'm going to have to walk and find an empty location, but I shouldn't have to walk too far. Okay. Of course, there's also the case where, here, let's just look and talk about some of the difficulties, or, you know, so let's say I say hash X equals 7. So when I say add X, X goes here, right? So I look at it and I see that it's empty. And in fact, I know it's empty because these are all preset to no. Let's just use the null symbol, the mathematical symbol. So initially this table is empty. I call add X. Let's use a different color for the non-null. Okay. And then maybe I call add Y, and I hash Y, and Y also equals 7. Okay, so I look here, and I see that X is there, so I'm going to look in the next location, and I see that this is null, so I'm going to add Y there. All right, and then maybe I add Z, hash Z equals 9, so Z goes here on a call to add Z. And then I say, well, add W and hash W equals hash X, which equals 7. Okay, so there's well, starting to get a little tricky. So I look here for, this is not empty, so I can't insert it here. So then I look here, that's not empty. Then I look here, and that's it, that's the end. but I still have a bunch of empty locations. So we're going to use the same trick we did with the array deck. We're going to use the modulus trick. So the next location I look is here. Right? So I'm going to go off the end of the array and then look in the beginning. And this one is empty, so I can put W here. Okay, so yeah, the strategy is very simple. If two things hash to the same location, or if I hash my element and I see that it's already full, I just walk. And I walk until I see null. And then I added it. All right, questions? Yeah.
What's the element data? Because now that it's forever, we don't know where it is.
Yeah, that's a good question. So let's say we want to,
We have to say offsets every time it works.
well, yeah. Oh, let's see if we say find, well, what do we want to find? Y? Well, we use the same thing, right? So Y hashes to 7. So we're going to look here. We did not find Y, but we did find something. And so, yes, we know because of the add algorithm that Y might be in the next location. So we look in the next location and we see Y. And we're done in this case. What happens if we say find, what should we say, S? And let's say that hash S equals 7. Okay, so is S in the table? Well, first we look here, we see that's not S, but then we're going to keep looking. We're going to see that's not S, and that's not S, and then we're going to wrap around and say that's not S, and then we're going to see that's not S, but also that's empty. So we're going to conclude at this point that S is not in the table. Okay, so we're going to walk until we see the first null empty location. And if we come across a null location, that means that the thing we're searching for is not in the table. All right, questions? Yeah. Sorry? Oh, is it not on? Sorry. Hello, hello. Oh, yeah, you're right. I'm sorry. All right. Okay, but of course, everything's working great. We've only added and find operations, but what happens if we have to remove? Well, let's make some space here. Well, this might cause problems. Let's say we want to remove. Let's say we remove Z. Well, Z hashes to 9, so that's fine. We look in location 9 and we find Z. And let's say that we put null back here, all right? And then we say remove W. Okay, so we have to do a search, right? We have to look for it. So we look here, W hashes to 7, so it's not here. And we look here, it's not here, and then we look here, and that's null, and we said if we come across null, that's the end of our find, right? But it turns out W is over here. So, okay, let's say we hit null and we keep going. And then we do find W. But the question is, what if W is not in the table? Where do I stop, right? So how do I know that I've searched far enough to be certain that W is not in the table? That's the question. And so when we remove something, well, it used to be that null indicated. If I come across a null, that means I don't have to search any further because if the thing that I was looking for was in the table, it would have been added here. But of course, that's not true of this one because when I added W, there was Z there. And so W got added further along. So we're going to have a second symbol instead of just null. we're also going to have what's called a delete. And this tells us that something used to be there, but now this location is empty. We can use it again. But this is going to help me in my search. So now on a call to remove W, I'm going to look here and I don't find it. I look here and I don't find it. I look here, I don't find it. I see a delete, which means that, well, I should keep going because it's possible the thing that used to be there when W was added was removed. So I'm going to keep going here. I'm going to look and see W, and then I can remove W and put a delete there as well. And so yeah, so we had our rule of thumb was basically on any call to find, whether, add, remove, and find all rely on find. We all have to do a search. But if I come across null, I've searched far enough. If I come across delete, I should keep going. And if there's something in that location, I should also keep going. Okay, so those are the basic rules that we have. Let's look at one more scenario here. Let's go back to a call to add. Let's say we add W again. Well, W hashes to location 7. So we look, W is not there, right? We're going to have to search for W first because this is a set, unsorted set interface. And so we don't want duplicates. So I can add W, but only if W does not exist in this table. So I start searching here. That's not a W, but it's not empty either. So I look here, that's not a W. I look here, it's a delete. So if I want to add W, this is a good location to do it. But I'm still not 100% sure that W is not in the table. So I'm going to keep going and see, oh, there's a delete here. Then I see, oh, that's null. So once I hit null, I can be sure we're going to, prove this. It's a very light proof. But for now, we're just sort of convincing ourselves that if I see null, that means the thing I'm looking for is not in the table. Because if it was in the table, it would have got added there. So I come across null, I'm done. At which point I can either backtrack or I can start over. And then once I hit this delete, I can add W there. All right, so that is the problems associated with it arise from remove primarily because I have some sort of search path. When I added it, I took some sort of search path, but if I remove something in that search path, then I have to remember somehow that there used to be something there. So we're going to use that delete character as well as the null character. All right, questions?
You have some really smart or not smart person going to add that. Like, you just put that as some protected type, then do an add and try to add that. Let's go.
Yeah, I mean, yes, you could make a mess. But del is like nil, generally, or a dummy. It's like a node, and it's recognized, not a node, but like actually, I don't remember how they implement del, but it's regardless, if it's an object, maybe it's generic. I'm gonna have to look it up, but I think they just make a version. They just say like, I'm declaring e del. And then this is just how we identify it is it's a memory location, right? So if I compare an object, I can say like, well, I have to be careful. Yeah, no, you're right. And there are like sort of things in the code that that account for this. There are extra checks to see. So if we have an object O, we check to make sure that it's not equal to del, and then, and then there may be or O dot equals whatever. But yeah, you're right. That does require some extra protection. Yeah. No, it's a good observation. Other questions? Yeah.
Stan, what does it mean to have two copies of the same object, but it's fine? Like, what does it mean to have two copies of the same object in the system?
Right. Okay. I'll hit on it now and then we can continue it later if you want, but well, students, right? So students all have a unique ID, a student number, right? So I have maybe I make a student here. And the number is student number 1. And then they have a name and whatever, GPA. At some point, but this exists in memory, right? This has a memory location, let's say a hexadecimal. It would be a lot longer than that, right? 64 bits is, what is it, hex? It's 8. No, what is it? It's power 16, I forget, I don't know. But yeah, these are very long addresses, typically represented in hex because it shortens it up a bit, although they're still pretty long. So this is the memory location, and then at some point I just make a second student. I make a copy because I want all of the students who are on the honor roll and so I make a copy of the same student, but it's in a different memory location. All right, so let's call this student 1 and student 2. And the consequences of this are that, well, I want these to be equivalent, but of course, S1 and S2 are variables. So if I say, is S1 equal to S2, or maybe like, assuming that this worked and printed out true or false, well, this would print out what? Would this be true or false? Be false, eh? Because what this is really asking is print is OXAA equal to OXAB. It's comparing the memory location. So it's saying, are these exactly the same object? So this would print false. But if I said, well, generally speaking, we have this other function on most objects, this equals. If you don't implement it, I believe it's equivalent to that, right? So if I don't implement equals, it just checks the memory location. But if I implement equals, then what I really want to do is say, is the student number the same? Is the student number of this student equal to the student number of this student? And in which case, that should return true. Right, so this is, maybe they're not the exact same object in memory, but they are, I want them to evaluate to the same thing. Whereas this is asking, are these exactly the same two objects in memory? Like, are they precisely the same object? Are they, so this would return true if I said this, or if I pointed S2 at this one, then they would return true, but if they're separate, they would return false. So that's important to know, especially when you're using data structures. This is a true story. So on the ODS code, actually, trying to remind myself to tell Pat, because there is a bug. This is the bug that I put out an announcement about. So what it does is it does something like this. It says, what are they? Iterator. you don't have to know this, but this is ITA and then ITB. And it says A dot iterator. And then there's the bug or the typo or whatever is that, well, I have a list A and a list B, but they both come from list A. So these iterators are, not only are they equivalent, they're exactly equal. And then later on it says if, well, it's an assertion, right? It says assert ita.next equals itb.next. And it uses this. It actually might be not equal to, but the same thing happens. So what happens is that actually these are exactly the identical things in memory. So this returns true. But if you fix the bug, if you say, well, actually, this is supposed to be list B iterator, then this should return true, but it returns false because actually what we want to write here is like ita.next dot equals itb.next. Right? I don't know. It's kind of a mess, but yeah, so this exact scenario is the bug that is in the ODS, the list identical function. Has this bug exactly, and every single time I teach this course, I run across this bug, and then I forget to tell Pat about it. And then the next year I come across it again. I say, why is this not? Oh, here's a bug. I fixed it. And then all of a sudden, these two things that are equal, this is returning false because these are integers, but they're in different memory locations. And it was a bloody mess. Anyway, I have to remember to tell Pat. So yeah, that's a bit of a, again, worth going into because when you're programming with data structures, these things are important. You should be using the dot equals whenever possible. Questions? Yeah, so what was happening is that this should return true, right? We want to see is this integer equal to this integer? And it should return true. These lists should be the same. And it does return true, but only because we have another error up here, that they are identical. They are in the same memory location. So when you fix this bug, all of a sudden all your tests fail because now this, yeah, it's a different bug, but they work together to like give you a false sense that things were passing. But yeah, and every semester this thing gets me. Every time I've taught it, I've been like, what? It's in the if you download the testum from the ODS library and you use list identical, so it takes two lists and check to see if they're identical, then this bug is in there. Yeah. So I have fixed the bug on the code for assignment 2 because I take a copy of list identical and it's there. So I fixed it, but yeah. Actually this bug is still in the blocked list. But I fixed it on the server. Anyway, questions? Okay, so that's a good little aside, but okay, so back to linear probing. So a couple things. So we're gonna sort of go in a little more detail about how to implement these things, but also, as you should imagine, the performance of this is going to depend on how quickly we run across a null, right? So maybe keep that in mind, but so yeah, we're going to implement the unsorted set interface, so add, remove, and find. We're going to use null values for array locations where nothing has ever been stored. So when we make a new table, it should be filled with null values. And then a del value for a location where data was there previously, but it's been deleted. In addition to tracking actual elements, N, we have a second value Q, because again, the number of null elements affects performance, right? We want to have a lot of null elements. We want to stumble across them all the time when we're looking for stuff so that these find operations don't take a long time. But so on a call to find, if I see a del, I actually keep going, right? So dels, even if I have an empty table, but there's a lot of dels, my performance will go down. So we want to keep track of the number of data elements plus the number of del elements that are in there, right? So in this case, this table, I have n equals 6 data elements. So 1, 2, 3, 4, 5, 6. But on top of that, I have these two dels. So my Q is equal to 6 plus 2, which is 8. Right? So Q is N is how many elements, but Q is a measure of like how many nulls I have left in some sense. Okay. So on a call to remove, so I think yeah, I mean, this just rehashes what we already went over. Yeah, so on a call to remove, we're going to hash. Yeah, if we call remove W, we hash W, we see that that location is full. But this is, I mean, ask me to stop if you want, but we already sort of went over all of these cases, or at least most of them. But yeah, so just a reminder, I guess, on a call to hash W, on a call to remove W, we would start here. We would look and look and look. And well, we run off the end of the table, so we keep going over here, and then we find W. Once we find W, we're going to replace it with this del element. And that's it. Then I'm done. A call to remove Y. Yeah, all right. So this, again, I'm going to skip some of this because we sort of just went over all of this in the other example. Let me see where's a good place to. Yeah, I guess. Yeah. So just to sort of review, if we're adding something and we want to search, we have to search for the thing. And if we come across a del, we have to keep searching, right? Because this is the unsorted set interface and we don't want duplicates. But when we add, we actually kind of do want to put it in this location, right? This will help keep our table performing well, right? If we replace a del with a variable, then we do not have to increment Q. And Q is a measure of how cluttered our table is getting. All right. So yeah, to stay efficient, we want many null values. And essentially, we want our table to be at least half full of null values, right? So that means on average, every second location is going to be null, which means that even if we get unlucky and we have a bunch of elements that cluster together, we still should not have to search too far for a null value, right? So we want a table that is at least half full with nulls. Our hash function only works with tables that have some power of 2, their size. So yeah. All right. Okay, so yeah, I skipped all that stuff, but we did talk about that with the on the previous slide. So if you want to review it for yourself, there's sort of some examples that kind of go through the same things we went through. But let's look at a couple implementation details. So in our linear hash table, we want, of course, an array of type T, if T or E or whatever it is we're storing. We want the number of data elements in our table. We want the number of non-null entries, and we want to store the dimension of the table. That's going to help us with the hash function. So when I want to find something, I hash it, and then I just keep looking. And as mentioned, there is this, right? So the first thing we have to do is check to see that it's not a del. Now, we do that in addition to seeing if it's equal to the thing we're looking for. Because depending on how objects are defined, right? If I just say T del, well, there might be a default constructor for whatever T is. And that's going to give me some actual default values, like maybe a student number or something. And it might be the case that I have an actual data item, and that data item will return true if I say x dot equals del, right? So like you were saying, there's no guarantee that if I say x equals del and I don't know the type beforehand, maybe this returns true sometimes, right? So we include this extra check to see like, hey, it better not be equal to del, as long as it's not equal to del. But also, it looks like it equals the thing I'm looking for, then I return that thing.
X is not del.
Oh, sorry.
So if my array element is equal
Should
to
be
X,
T.
it's probably not del because it's equal to X, which is not del. So I still don't understand why you're checking that. Because X is not del. I'm not looking for del.
Because equals, again, even this might return true even if I have so let's think of an example. So I say T del, and okay, so we're storing integers actually, integer objects, right? So the compiler replaces T del with integer del. Integer is an object wrapper for the primitive int type. Okay. By default, del will be equal to 0. I assume. It's possible that it's not, but I'm pretty sure that's the case. And so now if I'm storing integers, maybe I'm actually storing 0 in my table. Or maybe I'm looking for 0. Am I storing 0 in my table? Well, yeah, I'm storing a 0 here, and anywhere else that I'm storing del, but I don't want that to return true, right? So that's the problem. If I said, and then I say find 0, then this will return true when I see a del, but I want to make sure that it doesn't.
Is it del or not? It's 0.
Well, no, if it's del, that's the thing about del is that how we test for it is using the memory location. So that's this. So we see, is this actually equal to because yeah, if I'm storing more than one del, like let's say this is also del, well, these are actually the exact same object, like they're the same memory location, everything. So if I do this test, it will return true if it's del, but false if I say if it's 0, right? Yeah,
Since if you say it's not this object del.
that's right. I'm saying this is not the object del, but like if I put del in this equals, it would return true, which I don't want to have happen. Yeah. So yeah, that's sort of, it's funny that all this came up organically, or at least at this time, because yeah, this is completely relevant, this memory model of Java. And when we use this, so this not equals tests memory locations, right? So this tests memory locations between objects, and sorry, this also tests memory locations. Whereas if I want to test if objects are equivalent, I would use x dot equals y, or I could put a not here as well, right? The not just reverses the true and false. Very not super important for like the principles that the linear probing works under, but if you're implementing it, this is very important, right? This is one of those bugs that would be very hard to find. All right, questions?
Size of your table with the hash value, but also your expected total number of data points. So like if you're only expecting 10 things, then a table of 0 to 9, well, that's sufficient. And if you're expecting, or you maybe want to have a table of at least 20 to follow the hash key law.
Yep.
But then also you want the hash function to kind of match, so it has like a good spread over that.
Yeah.
But then, like if you think of a bank, we're using the hash value of, okay, they have 1 million customers, and how do they, or you want to find this person up by hashing, per se, you gotta have the hash value kind of match. And is that something that they're looking to, or they just have this massive hash function that works for all kinds of things, and they do module size of list or something?
So you're talking like big databases, huge database. Yeah, yeah. No, hash functions work great, apparently. I mean, I know, or at least Google used to swear by them, and back when it was a big deal, actually, that they were storing the entire internet. Yeah, the hash functions work great on. I mean, even if so, we're saying like, our guarantee is that you'll never visit. If I do a linear search, it's never more than 3 items. Well, like if you're running on a supercomputer, like 3 items becomes like 3 million, right? Like a linear search is still no problem. Yeah, but so yeah, you can even have like hash codes that don't perform perfectly, but you're still going to get like really good performance, especially like for the size of what you're using. But yeah, they are like, this is hashing, and hash functions are one of the things that are actually used a lot, right? It's this find operation of just like do some math and then, oh, that gives me the thing I'm looking for. Like that's a huge plus. Saves a lot of time. Oh yeah. Yeah, well, I mean, you can always use this, but yeah, then when you use something that's sort of publicly known, you can get a bad actor can say, ask to store a bunch of things that they know is going to hash all to the same location, right? So if they know your hash function, they can break your server basically. So they store everything and everything gets stored in one list, and then everything that every time they look for it, it takes a linear time. And yeah, so the actual hash functions that get used at a place like the bank or Google are, I imagine, proprietary and not given to the public. Probably some crypt. Yeah, I would guess that cryptography is involved. Yeah, because yeah, it's a huge deal. If you know somebody's hash function, you can ruin their life, basically. Yeah.
Power W, but we have here 10 elements.
Yeah,
Them.
just for demo. Yeah, yeah. So yeah, sorry, but I have to make these, space versus, um, accuracy versus clarity kind of judgment calls. So yeah, if I add, I resize if my table is getting too big, right? And how do I know too big? Too big is now the Q value. So again, I want to make sure that at least half of my elements are going to be null. So I'm assuming in the worst case that the thing that I add is not going to be added to a del, it's going to be added to a null, and in which case this means that I will have less than half of my null values, so I'm going to resize. Even though I may add it to a del, but even if I'm close, I'm going to resize. If I add at a location that is equal to null, then I increase Q. If I add only at a location that is equal to del, then I would not increase Q, but I would increase N in both cases. But yeah, this is not going to get too deep into that, but any questions? Remove, similar. Again, there's this, we have to do that extra check. Again, the reasons are sort of complicated and have to do with memory and stuff. But basically, the thing to point out that is sort of new here is this resize function. So if my table is like 8 times the size of my data, then I want to resize and I'm going to end up shrinking it. Okay, and so yeah. Search for the thing I'm going to find. If I find it, I delete it. And this is just the advancing modulo without using the modulus function. All right. All right, so that's linear probing. That's the a little bit of talk about memory, but the basics of it, the fundamentals, I think we'll save for next class is next week, eh? So yeah, next week we'll prove correctness. It's not that hard. We will just verify the things that we suspect that this works, and then we will look at a little bit about the resize. And so yeah, but we'll save all that for next week. So Thursday, I expect that assignment 3 will be out tomorrow. Perhaps not. Regardless, office hours are moved up on Thursday. So it's a half class, basically. You write your test and then you can go, but office hours are directly after the test. Okay, so at, where was it, 1:30, so 1 o'clock. 1 o'clock, the office hours will start. If anybody wants help with anything, possibly assignment 3. But otherwise, yeah, I will post the marked up practice test. It's not great. I know it's a bit of a mess, but maybe some of that stuff will make sense. And yeah, otherwise, yeah, good luck. I think Ishtiak has I have office hours now. Ishtiak has office hours tomorrow. So if anybody wants help with any of these concepts, we're here. Evan should be here too as well. Yeah, I will be posting it to Brightspace. I will have to remember not to delete it and close it, but yeah, I'll post it to Brightspace. So yeah, that's it. I'll see you guys Thursday, if not before, but yeah.